All right, so I guess as a part of all of this, let me just dive into stuff that I used to know that I want to brush up. So let's get into the Ising model. I just sort of found a few different clips over here. The Ising model in Python, no. And then just the generic Ising model. So, let's start off with
The
this
goal
one.
here is to introduce the Ising model without
Okay.
going into details about its solution.
All
Suppose we
right.
have a system of n sites with two possible states. That
All
could,
right.
for instance, represent localized spins 1/2. That can be either
Right.
up or down.
Okay.
Importantly, any two neighboring sites are coupled via an interaction -j. In this
All
way,
right.
a positive value for j favors parallel alignment of the neighboring states.
Right.
Additionally, we could think of a term to manipulate the state at each site individually. In the case
Right.
of localized spins, this can be achieved by an external magnetic field. For a thorough discussion, check out our videos on non-interacting spins. Basically, in
Okay.
the presence of a magnetic field, the magnetic moments will tend to align. The system
Okay.
can be described in terms of this Hamiltonian. The first term corresponds to the system coupling to an external magnetic field, B.
Okay, that's B.
We rotate our point of view so that the B field points in Z direction. GS
Z
and
direction.
UB are just numeric factors. If you want to find out more, they are called spin G factor and Bohr magneton.
Okay.
Note that the Hilbert space is spanned by states of all possible combinations of spins up and down at each side. Therefore, the Pauli matrix sigma zi reads up.
All right. Let's see what the Hilbert space is. If I'm going to get back into it, I might as well brush up properly, right? So Hilbert space in mathematics, a Hilbert space generalizes the notion of Euclidean space. It extends the methods of linear algebra and calculus from the two-dimensional Euclidean plane and three-dimensional space to spaces with any finite or infinite number of dimensions. A Hilbert space is a vector space equipped with the inner product operation, which allows lengths and angles to be defined. Furthermore, Hilbert spaces are complete, which means that there are enough limits in the space to allow the techniques of calculus to be used. A Hilbert space is a special case of a Banach space. Yeah, I'm kind of remembering this a little bit from undergraduate. All right, so let's keep going.
Up minus down at side I. That's all we.
So psi zi is equal to up minus down for I, and then that's summed over I. So for the number of spins that you have. So okay, this is the. I guess that was the Pauli Z matrix or Z matrix.
We need to understand the second.
So that would be 0, 0, minus 1. So it would be 1, 0, 0, minus 1 if it was a matrix summed over n. If I was 1. Huh. Okay.
Term as well. It contains the coupling of neighboring sites, a sum over all nearest neighbors, and the product of sigma matrices at.
So sum over all nearest neighbors. Okay, so ij, all nearest neighbors. So this means 1, 2, 2, 3, 3, 4. Okay. So this is not 1, 2, 1, 3, 1, 4, and then, okay.
Side I and j. As mentioned, a positive j will favor neighboring spins to be parallel. It is now time to.
Okay, so neighboring spins interact with each other, but they don't skip a particle.
Think of different geometries in which n sides may be arranged. In one dimension, it is a simple chain. that could have free or periodic boundary conditions. The
Right.
1D Ising model is solvable with pen and paper. The solution shows that it has no phase transition. The result was reported in 1924 by Ernst Ising in his thesis. The problem was originally posed by his supervisor, Wilhelm Lenz. That's the same physicist we know from Lenz's rule. In
Okay.
2D, there are multiple ways to construct a lattice, which differ in the number of nearest neighbors. A simple way would be a 2D square lattice. For historic reasons, the exact solution for the 2D Ising model was given only much later in 1944 by Lars Onsager. The Ising model in 3 and 4 dimensions is still under investigation. However, the limit of large dimensions can be described by a mean field approach. That is, one side is described in an effective field construed by the surrounding sides. The Ising model is still widely discussed despite of its age. A reason is surely that many problems can be mapped to the Ising model. For more details on how to solve the Ising model and where it might be applied, stay tuned. That's pretty.
Also, an Ising model is like one of, if not the simplest model in which you can start off like modeling a system. So for quantum computing, for example, you would want to start with modeling an Ising model and see what the results are, and then work your way up to more complex, I guess, molecules.
Quantum computers, which will be ideal, will only require knowledge of computer science. But the quantum computers that we have today require a bit of understanding of the underlying physics. So we have to go through a classical model of statistical mechanics, which is called the classical Ising model, to understand what happens in some quantum computers that we can use today. So let's start by introducing a spin system. A spin is a two-state system. So for instance, you can think of a magnet having north face pointing up or south face pointing up.
Right.
And you know, if you take two magnets and you approach them, then they want to anti-align.
Right.
So this will be their optimal energy configuration.
Okay.
So if you identify random variables with them, for instance, this is some random variable sigma 1, this is some random variable sigma 2, and you say that the north face pointing up is the value +1, and this is the value -1,
Okay.
then you can write down that the energy of this system is, say, sigma 1 times sigma 2, and in this case...
Oh, it's pretty cool. I mean, he's essentially recording himself through glass and then writing writing on the glass. And then I'm guessing he's writing as is and then obviously flipping it. He's not writing it back to front. Interesting.
It's going to be -1, so we look for the lowest energy solution.
Okay.
This is what nature naturally finds.
Okay.
Now if we add one more magnet, then that is also going to anti-align with its nearest neighbor.
Okay.
So this is going to be +1 for some sigma 3. So we can write another term here, which is sigma 2 times sigma 3. And we can write that as a sum over...
Right, and this is in the absence of any magnetic field. So B is 0, so you only have the sum over the... Okay.
our nearest neighbors. So this notation stands for nearest neighbors. And we are going to have sigma I, sigma j. So this term describes the energy of this system, and we want to minimize it. But nature naturally minimizes it.
Yes.
Now, let's make it a little bit more complicated.
Let's
and assume that there is some wall that you can control. So with this,
there is the wall.
You can change the strength of interaction between the individual pairs of magnet. In other words, you can change the coupling strength between them. So we model this by having some coefficient with each of the pairs of the interactions.
Okay.
Now to complicate it even more.
Backward E, or is that a different thing? Backward E means like everything, but okay.
we can add an external magnetic field below each and every one of these individual magnets, which in theory can be a lot bigger than the interaction strength between the magnets.
I can't help but be distracted, but it looks really painful to stretch out over there. I mean, to do this on a daily basis, this must be a really painful way to write.
Say each of these are north.
Right, so you got a magnetic
up.
field.
So now if this magnetic field is strong enough, then it can flip, for instance, this magnet upside down. So there will be some frustration between these two.
Right.
But the strength of this magnetic field will overwrite this interaction. So we model this external field by adding one more term here, which is going to be the strength of that field, Hi, times the actual sigma I value, the value of the random variable in that spot.
Right.
So this is actually a very hard problem to solve for nature.
And then I guess if Hi is the same, so it's a uniform magnetic field, it just becomes H.
Because what happens that if you look at the energy landscape of this problem, and what can happen is that, for instance, the magnets naturally align, they flip, but they might get stuck in some local optimum. So it's possible that by overcoming this barrier, they will be able to attain a better configuration, which is the actual lowest energy solution. But since there's nothing, there isn't enough energy for the system to hop out from here, it's stuck in this local optimum. And this is exactly the same kind of problem that we see in computer science in certain NP-hard problems. So if you look at something that's called the quadratic unconstrained binary optimization problem, it actually has a very similar form. You have binary variables, and you have some interaction strength between them. They have coefficients. And you also have a bias term affecting individual random variables. And on a classical computer, in the general case, this takes exponentially many evaluations to find the global optimum, because you have the same problem. You would otherwise get stuck in some local optimum. So there is this very natural correspondence between what is computationally hard and what's physically difficult to solve. And just by convention, we typically put a minus sign here, and we change this into a minus sign. So the actual coupling strengths are opposite sign to what I described here.
So essentially, this is an NP-hard problem. So he's saying that NP-hard problems can be mapped into a Ising model. And if an Ising model can be, if you can program an Ising model into a quantum annealer, which is what D-Wave have done, and you can solve it now, then already right now there is a set of NP-hard problems that can be efficiently solved with quantum computers. Okay, let's keep going.
But apart from that, this describes the energy of the system, and the operator or this equation that describes the energy of the system is called a Hamiltonian.
Very good. That is the Hamiltonian. Let's move to the next one, chapter 10.
We introduced a simple model from...
So transverse field Ising model, classical Ising model rewritten. So sigma z is 100 minus 1. Sigma x is 0, 1, 1, 0. And then if you multiply the Pauli matrices, you get these matrices. Sigma 0, 0. Yeah, that's right. Yep. That's the Hamiltonian. Commuting Hamiltonian. Commuting Hamiltonian. If it's commuting or non-commuting. Commuting with what? Okay, what is commuting? It's been a while. Commuting operators in quantum mechanics. In quantum mechanics, commuting operators are crucial because they share a common set of eigenstates allowing for simultaneous measurements of the corresponding observables. A complete set of commuting observables is a set of commuting observables eigenvectors can be used. See, it's a set of operators. It's commuting operators. So is the Hamiltonian not an operator? Because essentially it's a square a comma b equals 0, square brackets equals 0. That's commuting, meaning it's independent of which way you do it. Okay. So my intuition is sort of right. Let's see what he has to say.
Statistical mechanics called the Ising model.
Yeah.
But there's nothing quantum happening in it.
No.
So we are interested in quantum computers and their relationship to quantum many-body systems.
Right.
So we actually have to look at a quantum many-body system.
Right.
To get there, first rewrite our classical Ising model in a more quantum mechanical form.
Right.
So in what we introduced in the previous video
Right.
was this Hamiltonian of binary variables.
Right.
So we know that in quantum mechanics we have states and operators acting on these states.
Right.
So let's look at a particular operator that could act on, say, a qubit.
Okay.
So I defined this sigma z operator, which is called a Pauli matrix. It's the Z Pauli matrix. It has this very simple form. And when you apply this operator on the zero ket, you actually get the zero ket. It doesn't do anything to it.
Right.
Or you can think of it as adding a +1 multiplier to it.
Right.
And if you apply it to the 1 ket, then the 1 ket picks up a sign, a minus sign. So basically it applies -1 to it.
Right.
So by applying this operator on these two basis states, you can reproduce the effect of getting +1 or -1 as a probability amplitude before the actual state.
Right.
So the quantum mechanical form of the classical Ising model is exactly the same as what we have seen, except that we have
He's doing a great job. This is so good. Good job, man. This is really, really nice.
Operators here. So now all of these are sigma z operators acting on a particular qubit.
Right.
But since this is now a large operator,
because you've chosen the z direction, so
what we want to do is calculate the expectation value of this, because we are interested in the energy of this system and not an operator. And when we are talking about measurements, we saw that if we sandwich the measurement operator with the bra from the left and the ket from the right, then we get a scalar value out of it. And we are doing the exact same thing here.
Right. That's
so the energy or the expectation value of the system is exactly this.
Right.
So this can be calculated very easily.
So why is it called a commuting Hamiltonian?
This Hamiltonian is commuting, which means that every single one of these matrices commutes with one another.
Every matrix commutes with each other. So sigma z commutes with sigma z, sigma x, x z, z x, 0, 0. So if you commute these two with each other, x z minus z x is this minus that. So you'll get -2, -2, and then 1 over square root times 2, a half. So you'll get 0, 1. You get minus what? Well, you don't get 0. Hold on a second.
Now, when you have a commuting Hamiltonian, that's actually not very interesting from a quantum mechanical perspective. These correspond to classical systems.
Oh, because it's all z. Right.
To have any quantum mechanical effect, we have to add something more. And this is where the transverse field Ising model becomes...
Oh, classical and transverse field quantum. Oh, yes. Okay.
Interesting. Because what we are adding is one more type of interaction. A sigma x interaction, a transverse field interaction.
Transverse field,
so it's defined as this, and if you multiply sigma x by sigma z, or the other way around, you see that the result does not correspond, because here you have -1, here you have +1, and here you have -1, and here you have +1. So it matters in which order you use these two operators. In other words, if you add the sigma x to the Hamiltonian, then your Hamiltonian will no longer commute. So let's do that. So now we know that this is the classical Ising.
Right, that's the classical.
Written in a different form. And we can add this transverse field with, say, some GI coefficients as such. So on each side, this transverse field would act. So what does this mean that you have a transverse field? So to understand this, we have to look at the eigenvectors of the individual operators, because the eigenvalue of this operator will correspond to the angle.
Okay, so in the simplest one, this is 0, and you only have a transverse field.
So the lowest eigenvalue will correspond to the lowest energy for that particular operator in that site. So for the sigma z, it's just 0 and 1.
Right.
So it's +1 or -1, exact same thing as the classical Ising model.
Right.
And if you look at the eigenvectors of sigma x, it's one of the two states of the equal superposition.
Well, it's so crazy when you spend a significant chunk of your life focused only on this, the stuff that hits your brain, because I remember doing the, creating the matrices from the eigenvectors. Because you just multiply the eigenvectors with the transverse of the eigenvector, and you add them up, and then you get 1, 0, 0, 1.
In other words, when you try to minimize the energy of the system, this term tries to push it into a superposition, whereas the sigma z interactions are trying to be deterministically either 0 or 1.
Right.
So this is where you get this quantum effect by pushing it towards
very elegant explanation.
A superposition and having this non-commuting term.
Really good. I really like the way he's introducing intuition immediately. This is really nice. I'm definitely moving on.
Hi, I'm Adam, and
right.
I made an.
No, I like the way he's explaining this stuff.
Hello, I'm Roger Malko. I'm a physics professor at the University of Waterloo and the Perimeter Institute for Theoretical Physics.
Okay.
Today I want to talk to you about quantum many-body physics and its relationship to quantum computing, physical systems such as quantum chemistry, materials science, and numerical strategies for tackling the sort of quantum many-body.
So quantum many-body physics. So I did like the way the previous guy had set the tone. So I'll be honest, it's kind of jarring when the instructor changes, because you're kind of used to a certain way of thinking. What is the behavior of n interacting particles, atoms, nuclear physics, quantum chemistry, materials, quantum computers, electrons, atoms, devices, Schrödinger's equation, IH bar d by dt of psi is equal to the Hamiltonian times psi. N is equal to 1 is a hydrogen atom, and 2 is a helium atom. And for a quantum computer, example, 2048-bit RSA Shore, n needs to be greater than 4000.
Problem using classical computers. So quantum many-body physics is the study of essentially interacting particles, when these particles behave according to the laws of quantum mechanics. I'm going to use the notation n for the number of interacting particles that we're in.
So overall, this is going to help inform you and guide you as to why I think at the end of this lecture series, it'll give you a really good understanding of why quantum physicists and people in quantum information theory keep talking about 1 million qubits.
Interested in whatever it is in terms of the physical system or the logical circuit that we're studying in terms of physics, chemistry, or quantum computing.
Right.
So the main central question for quantum many-body physics is really what is the behavior of n quantum particles, and I say particles in quotation marks, but n quantum species, when they interact strongly with each other, right? This is a situation that we encounter, like I mentioned, in many different quantum systems. And by systems, I can mean either one or n equals one or n equals many of these interacting species. So we may be used to thinking of, say, for example, atoms or molecules or the nucleus of an atom, where many of these quantum species interact and move within potentials and so on. So in the realm of atomic, molecular, nuclear physics, this n, the fundamental
nuclear physics,
number of quantum species that interacts, could be something from, say, 1 to 10 to hundreds or something like that,
right?
Depending on the species of the atom, the type of nucleus that we're interested in, and so on.
Nucleus.
So, say 10 to hundreds. In quantum chemistry, we're taking these building blocks, nuclei, atoms, and we're building up more complex.
See, it's nuclei. It sounds a bit funny saying nuclei if it's not even spelled that way, right?
Molecules. Because of like a separation of energy scales, we're essentially looking at possibly different interacting quantum species. We may not be interested.
I'm giving this guy a hard time for no reason.
in exactly how the protons and the neutrons interact, but we may be more interested in electronic degrees of freedom, where these electrons form things like valence shells and so on. Again, for n's between, say, tens to thousands.
Tens, thousands.
Quantum species. In materials science, condensed matter physics, solid state physics, we start building up this notion of many bodies to sort of the macroscopic scale. And what is the macroscopic scale? It's really the idea that we have many interacting, say, electrons, or many interacting atoms in a fluid. And in materials, we can go from, devices that trap atoms in clouds of 10 to the 9, 10 to the 11, maybe more, to the case where we have something like Avogadro's number. So n is typically less than or equal to something like 10 to the 23.
Avogadro's number. Man. It's been a while. Is a dimensionless physical constant known as the confused with the constant. Both are named after the Italian physicist. Okay, what's the what? It's got a Wikipedia. It defines the number of constituent particles in 1 mole. So essentially, if you're dealing with 1 mole, you have about these many particles. Nice.
So the fundamental thing that we're interested in terms of quantum computing is sort of what are the comparable ends to these, I guess, more traditional fields of physics, and how do we study the quantum many-body problem for such large ends? So for quantum computers, we ask ourselves, what are these ends? What are the equations of motion, or the equations of evolution that govern the quantum behavior of the system? And how do the building blocks that come from, say, atoms, nuclei, molecules, chemistry, materials, and so on, build up to give us these things? What I'm mostly going to talk about in these lectures is the quantum number associated with the, say, a single electron, which we know has a charge, maybe minus e, but also has a spin. So when I say spin, I'm often referring to that quantum degree of freedom that's related to fundamental angular momentum, say spin equals plus or minus a half.
Yes.
In atoms, we could think of a higher excited states, or we could have higher spins and so on. We could also have atomic positions and momenta and so on. All of these give more and more quantum numbers that we have to consider in this n-body problem.
Yes.
In devices, in a quantum computer, you may be interested in sort of the engineered qubit that gives rise to quantum behavior. And these could be things like superconducting circuits.
Hey everyone, big heads up, Paleo Valley's running a sale.
Bra, 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 bra.
They could be trapped ions, they could be cold atoms, and so on. All of these, you know, no matter what type of system we're looking at, all of these quantum particles are governed by essentially the Schrödinger equation. The Schrödinger equation gives us the time evolution of a quantum system. And by system, I essentially mean this object here, which is the wave function. So the wave function is the quantum state of the particle or the system of particles. Its time evolution is governed by this equation, and we're typically interested either in how, how an electron or an atom or a qubit behaves at some later time. We're interested in this ability to predict its later time. Its behavior at a later time. This is a very difficult problem. So for example, to see how difficult it is, we can take the case of n equals 1, where I've taken a single electron and I put it in a potential that is generated by a proton. This is the hydrogen atom. So imagine I have a proton, and orbiting around it is this electron. If I just consider this one-body problem, which is really the electron feeling the influence of the proton, that's essentially something we can solve almost exactly. You know, the time evolution of that system can be essentially determined in closed form. It's something we do in third-year undergraduate physics and quantum mechanics. If I moved on to the n equals 2 case, which is the helium atom. So in the helium atom, I have a nucleus of 2 protons. And I have 2 separate electrons orbiting around that nucleus. There's no known exact solution for that in closed form. So even in this very simple case of a helium atom, there's no way that we can write down the equations of motion that govern.
Now that is how shit classical computers are. As soon as n goes to 2, as soon as n is only 2, you're like, oh my god, I'm fucked. I don't know. I have to do all of these approximations.
The time evolution of the electrons. So you can imagine that analytical solutions for problems like these are very difficult. So how many qubits can we imagine that we can solve for the equations of motion for? And how many qubits do we need to solve for the equation of motion for the type of quantum computers that we're interested in building? Well, there's many different types of quantum computers.
Well, roughly 1 qubit for every degree of freedom per particle. No?
Computers, and there's many different sort of numbers of ways you can imagine building up
plus fields, etc., etc. Okay.
Qubits to do quantum information processing tasks. So one benchmark would be a quantum computer that can crack Shor's algorithm, say for example for 2048-bit RSA encryption, which is either current encryption or future encryption for things like your cell phone. So the smallest number of qubits required to break 2040-bit RSA encryption using Shor's algorithm is believed to be somewhere around 4,000. Okay, so it's roughly double the number of bits in the RSA key. These are logical qubits. Qubits, logical qubits. What one must understand is that one logical qubit is often made up of several thousands, or in the best case scenario, hundreds of physical qubits. So one logical,
because of error correction,
is say 100 to 1,000
error correction. Qubits. Well, at least right now with current.
This gives us a number of somewhere around 5 million. So the quantum many-body problem that we're going to solve for a typical case scenario of a quantum computer that's implementing Shor's algorithm for 2048-bit RSA is somewhere in the vicinity of, say, 5
million.
I don't know what I said before, but I meant 5 million.
So excellent. This is really good. It was excellent. It's a great way of getting people on board, of understanding why everyone talks about 1 million qubits. It's sort of like rough estimate. But what you need to understand is that when he says it's, one logical qubit is about 100 to 1,000 physical qubits, he's not talking about the qubits that, Google has. He's talking about qubits that are much, much better than Google's. So, even if you had 5 million of Google's qubits, you would not be able to do this.
Okay, so this is the essence of the quantum many-body problem as applied to essentially quantum computers.
That was really good. You did a great job. So I'll keep going.
Let's focus our...
So many-body behavior of spins. So consider a spin qubit as half going up. Spin vector of x, y, z. Interactions. So this is your Hamiltonian. The z optimization problem. They're all next to each other. 2 to the n states. So if you go at 40, it's roughly 10 to the 22. Physical distribution. The probability is 1 over x. Boltzmann constant. Right, that's the Hamiltonian of x. It's the distribution. Right, where z is equal to the sum over the Boltzmann, and what is m here? I don't know. The mean position, I guess. So the mean distribution, the mean of the distribution. So quantum h is equal to sum over j minus hix. You put the x in there. You do the same with the spins. So you replace Pauli with spin. Solution, diagonalize the Hamiltonian to the order of M3. If n is equal to 30 to 40, then you've got boom. Okay.
Our study of quantum many-body physics on the simplest quantum system, which is the quantum number associated with spin or angular momentum, for example, of the electron. This neglects all other complications due to position, momentum, charge, spin-orbit coupling, hyperfine splitting, all these things that occur in electrons, and only focuses on the single object, which is the spin. We'll consider spin 1/2, which gives us an effective two-state quantum system. We can consider, in some basis, the spin, for example, of an electron to be, say, up or down. So a quantum spin has angular momentum properties, so you can think of it as being a vector with different components. And we can simplify the many-body problem even further by just considering a classical spin that only has, say, for example, an SZ component. So we pick a preferred axis for the angular momentum, and let's consider interactions between n spins that just occur between the z components of their angular momentum. So that interaction could be, for example, SIZ dot S.
Okay, I think this is really good, and as browsing through this is like over 33 lectures on this topic, and I'm not sure if I want to like react to all of them, but so far this is great, so I'm going to keep watching this on my own. You know what, why not? I'll just watch it.
JZ. And I could form a Hamiltonian, which is the fundamental object that governs all the time evolution in the Schrödinger equation for a classical set of spins, for example, like this. So here's a sum over all possible pairs of SZ spins. Here's an interaction, which I've left arbitrary. And here's the interaction term between the two SZ operators, SZI, SZJ. This is referred to as something you've probably heard of, the Ising model. The Ising model is the sort of simplest model of interacting spins, yet it is actually very, very highly complex in and of itself. So the Ising model is typically used to embody not only physical processes, for example, in the study of quantum magnetism or classical magnetism even, but it's used to encode optimization problems, which is something you may have encountered before. So you may want to be looking for example, the lowest energy state of this system governed by this equation, and that would be an optimization procedure. You're looking for the spin configurations of the n-body spins that give you the lowest energy as dictated by this Hamiltonian. So one way you can imagine doing that optimization procedure would be to look through all possible spin configurations. Let me call a spin configuration X, and here's an example. There's n different spins. They're in an SZ configuration or SZ configuration. And I look at all possible configurations and calculate the energy according to this Hamiltonian. So that's one example of a state or a configuration. I can imagine some other example. Up, down, down, up, up. That would be another example, X prime. And to search through all possible states would be to search through a very large number, a highly complex system of 2 to the n possible different states. How big is 2 to the n in this many-body problem? It's exponential, it's very large. So 2 to the 1, 2 to the 2, 2 squared is 4, 2 to the 3 is 8. This escalates very quickly. If I imagine a system of only 40 interacting SZ components of spin, so classical components of spin, I get a number that's 7 times 10 to the 22. The reason I chose this number is this represents all the data that is currently stored on all of the Earth's computers. All of our computers, all of our hardware, all of our memory, the dark web, everything is approximately 10 to the 22 bits of information. So imagine searching through all those bits of information. You can quickly see that it's an intractable problem. Similarly, performing this optimization problem brute force, say, for example, finding the lowest energy of an Ising model, is a similarly difficult problem. When I get up to a number as small as 268, which is just a couple hundred spins, that number balloons up to 10 to the 80. The reason I chose 10 to the 80 is this is the number of all particles in the known universe. So if you imagine even wanting to store a state, sort of store, if you will, all the possible configurations or snapshots of configurations possible for models like this, you can see that it's essentially physically impossible. This illustrates the sort of high complexity of even the classical world of interacting spins. So obviously we don't do this when we study physical systems. In physical systems, what we do is we look at probabilistic distributions. So a probability distribution that governs, for example, the amount of spin configurations and the type that might occur, for example, in a magnet at some temperature. So you might be familiar with that as the Boltzmann distribution, where this beta here is 1 over Boltzmann constant times t. That gives us the probability that a configuration that I've labeled as x occurs at some temperature. And what I need to know essentially
to use the temperature, not the time,
is the hx, so the energy that's governing that configuration. This object here is the normalization or partition function. It's a fundamentally important object. And it essentially runs over a sum over all possible configurations. and is weighted by the Boltzmann weight. So this would run over all configurations x, let me just label it like this, from 1 to 2 to the n.
Mm-hmm.
So that partition function is a fundamentally complex object. In order to calculate it, you essentially have to do these almost infinite sums when n gets very large. And that, only through that procedure, only by performing that sum or that trace, are we able to calculate physical quantities such as the magnetization. So for example, if all of these were pointing up, I might say the magnetization per spin is 1.
Right.
I would have to calculate that for every single configuration, and this thing's weighted by a Boltzmann weight and normalized by the partition function.
So this is the partition function, which is a normalization. What was M again?
Spin is 1. Only through that procedure, only by performing that sum or that trace, are we able to calculate physical quantities such as the magnetization. So for example, if all of these were pointing up, I might say the magnetization per spin is 1.
Right.
I would have to calculate that for every single configuration.
Right.
And this thing's weighted by a Boltzmann weight and normalized by the partition function.
So normalized by the partition function, it's got a magnetic weight. And this would be the average magnetic field. Okay.
So that's a common problem that we encounter in physics and chemistry and so on. And it's really the realm of statistical mechanics and thermodynamics. So if you take a stat mech class or a thermodynamics class, you will get strategies for how to deal with these very large sums, typically in some sort of problem.
So at this stage, you might be getting anxious and wondering, how does this relate to the real world? And my advice would be to not get ahead of yourself. So just take it one step at a time. Look at this as sort of like a test pattern for creating a television or for aligning your TV. Like, before getting ahead of yourself and worrying about movies and films and stuff like that, first just get a good test pattern, optimize the test pattern. Once you have that process down pat, then you move on in complexity, which is why this is about the scale, this is about what people have been dealing with in terms of quantum algorithms for a long while, because until they actually have a quantum computer and can start solving these, right? Once you start solving these in a quantum computer, then you learn, is it actually possible? What are these surprises? Things like that. And then once you sort of learn to, once your brain adjusts to the fact that, oh, this is pretty easy to do and normal in a quantum computer, then once you've simplified or crystallized all of that complexity into just simple algorithms, then your brain starts to think about more and more complicated ways in which to build up these building blocks. So first, just get nice test patterns and get the basics, the foundations really nice and solid.
Probabilistic way. That was all classical. What I've done is ignored those two components of spin.
Right.
But imagine my Hamiltonian for my Ising model also had a quantum piece.
Right.
So an off-diagonal matrix element, if you will.
Right.
This is the actual Hamiltonian of the D-wave device, in some sense. If I restrict
and D-wave, if I remember correctly, was created by alumni of Waterloo. So, which is why the physics that is taught there is kind of goes hand in hand with what D-wave does.
The sort of arbitrariness of these Jij interactions. So what D-wave is doing is applying what we call a transverse field, or an off-diagonal field, in order to simplify the, if you will, the optimization problem for finding the ground state of this Hamiltonian.
Right.
So the fundamental difference between quantum and classical Hamiltonians is these are now operators.
Right.
The spin states, so which I represent as a basis ket, are vectors in this state space, in the Hilbert space. And an operator like the SZ operator is a matrix.
Right.
So this object, this quantum Hamiltonian, is a very large matrix. It's actually a matrix of 2 to the n, which is the size of the Hilbert space, times 2 to the n.
Right.
So that matrix, the solution, if you will, of the quantum many-body problem is essentially diagonalizing that matrix. It's taking that matrix and finding all of the eigenvalues and eigenvectors that are governed by the time-independent Schrodinger equation.
Right. Time-independent Schrodinger equation. So once you've evolved the time to a certain state, then it's time-independent. You're at a slice in time. And then you find out what the eigenvalues are. Okay.
Diagonalizing a matrix numerically for a problem like this is known to cost of order m to the cube, where m is the size of the Hilbert space 2 to the n. So you can see how...
Okay, m is the size of the Hilbert space 2 to the n. So the capital M is this m over here, which would have been nice if they defined it here. It has nothing to do with the little m over there.
This diagonalization procedure escalates very quickly. In fact, it escalates so quickly that state-of-the-art diagonalization routines, which are run on problems of high symmetry, typically can only reach an n, which is a number of qubits, of 30 to 40, say. What those diagonalization procedures give you then is an energy eigenvalue and also a state wave function, which is made up of a linear superposition or a linear combination of all of these possible snapshots that I talked about over here. So there's 2 to the n elements in this linear combination, each one of them which can have a complex coefficient. So the coefficient that is associated with this linear combination doesn't even have to be real or positive. We'll talk more about that. This difficulty of this problem and this small size that's typically achieved by even state-of-the-art diagonalization routines gives us the concept of quantum supremacy. So quantum supremacy is the idea that we can do better than this only with a quantum computer.
Right. Yeah, I'm just going to keep going. So it's 12, 13. Why not? This is fun,
Wealthfront
man.
offers a cash account.
So just kind of comments to make, which is because it's D-Wave and Waterloo, they're pushing the Ising model because that's the basis of their quantum annealer. And, you know, they were pushing for a long while to try to find practical problems that were relevant to, I guess, anyone. And just keep in mind that it looks like they're heading towards discussing a quantum annealer as opposed to a universal quantum computer. So their focus is on an Ising model and how do you create a quantum computer that's specifically designed to model and solve an Ising model. Yeah.
Finally, let's talk about strategies to solve, quote-unquote, the many-body problem. So we've talked about the many-body problem, the difficulties in solving it. So how, in practice, do we go forward for solutions of the many-body problem, both in physical systems and in devices such as quantum computers? Well, before I talk about numerical techniques like
strategies to solve the many-body problem, analytical approaches, perturbation theory, neglect interactions, numerical approaches, truncation and compression, stochastic, MCMC, Monte Carlo, right, okay, machine learning, 2 to the n images, big data problem, so supervised learning, unsupervised, reinforcement learning, and then machine learning characterized prep design.
Like
okay.
the extensions of diagonalization and so on. I just want to mention that there's a rich history of analytical techniques that have been used for decades to solve many-body problems in quantum mechanics. And those include things like perturbation theory, where you treat the electron-electron interaction as weak, variational principles like I talked about in helium, and other methods that maybe altogether neglect interactions or treat them very perturbatively in the regime where they are weak. And this has been very successful in semiconductor physics, solid state physics, and theory of metals, and so on. This is very important because we have to remember that our current silicon-based classical computing technology is in fact a quantum many-body problem. It's just one where you can neglect many of the electron-electron or spin-spin interactions that I talked about previously. So now as we move forward into 21st century quantum problems, where the electron-electron or the quantum interactions are important, these analytical approaches based on the neglecting those interactions tend to break down.
Right.
So in the strongly correlated regime of materials, quantum chemistry, and devices, we're much more reliant on numerical methods. So I mentioned exact diagonalization, which has an exponential scaling problem.
Right.
In many cases, that is still your best technology, if you will, for solving the many-body problem. Various numerical sort of approximations can be made, even in the regime of diagonalization, such as taking a Hilbert space or a spectra, an energy spectra, that's exponential in size, and finding a way to truncate that down to something perhaps that's polynomial in the number of qubits. These types of truncation, compression techniques where you modify the Hilbert space can have varying degrees of success based on whether or not sort of the problem is amenable to this type of truncation. If you're interested only in low-lying states, diagonalization routines such as Lanczos iterative solvers will give you better scaling than the brute force O to the m cubed that I talked about previously. Advanced methods such as the density matrix renormalization group involve sophisticated decimation schemes based on the entanglement structure of your wave function, and basically are known to work very well, for example, in one dimension. Another main sort of strategy for solving many-body interacting systems is stochastic approaches based on Markov chain Monte Carlo. So these require a statistical sampling of the configurations that make up the wave function, which I talked about previously. So in these methods, you imagine that some probabilistic technique samples configurations according to a Markov process, I plus 2. The problem with these stochastic methods is that the coefficient of the wave function for each one of these configurations has to be interpreted as a probability distribution. Only then can you update configurations stochastically, giving yourself access to estimators for quantum objects, which are basically just made up of, say, for example, the magnetization along that Markov chain. And as you know, the coefficient of the wave function in that linear superposition or that can be complex by nature. So there's many cases where stochastic approaches don't work in many-body problems. Where these methods do work, you can get n's in the thousands, say for DMRG. And for stochastic quantum Monte Carlo methods, you can get n's in the millions or more. So when these methods work, we should definitely use them. There's many cases where we know they don't work. And what we're doing now in physics, in computer science, in quantum chemistry, in academia and industry around the world, is turning to new approaches based on machine learning. The motivation behind using machine learning is essentially because if we take the spin configurations that I talked
essentially just let the neural network figure out whichever solution is best. I mean, there might be other methods that our brains have not figured out classically. So it could do a good optimization, and it could lead us to understanding whether there are other classical approaches that are more optimized than what we have currently figured out. But again, nothing's going to give you a better answer and a quicker answer than actual quantum simulation on a quantum computer.
Talked about in terms of either the Ising model or the transverse field Ising model, and we map these to
save thousands on the new revolutionary swims.
All right, here we go. More ads. Cool.
They're binary numbers, or say black and white pixels. We immediately see that this turns into sort of an image problem, in the sense that we can have a large number of images made up of these pixels that we're interested in processing in some way. So a big data problem from quantum mechanics can turn into a machine learning problem. There's various different strategies that we're used to employing in machine learning that we can turn to the quantum antibody problem. Supervised learning is when we have data with labels. So if we can take configurations and label them, say ferromagnetic, paramagnetic, quantum error correcting, or whatever, then we can essentially do many tasks in classification, etc., with supervised learning techniques.
Etc.
This, of course, requires labels, a priori labels.
A priori labels.
In many cases in the quantum many-body problem where we don't have labels, we would turn to unsupervised learning. Unsupervised learning might be looking at a quantum wave function and trying to find clustering or associative rules that govern the behavior.
Essentially say, you tell me if there's something going on here.
Unsupervised learning can also be taking measurement data, which is a measurement performed on the wave function, say a projective measurement collapses the wave function, and essentially reconstructing that wave function from individual images or snapshots. That's like a reconstruction of, say, a probability distribution in the classical case, or the full wave function in the quantum case.
I do feel he has to explain these a bit more. So, I mean, I kind of get the intuition of what he's talking about. But is he talking about a single snapshot? You put one in. So unsupervised learning means there's a lot of data points and you say reconstruct it. Okay, so it is a lot of data points and okay.
These reconstruction techniques based on machine learning are now being studied and compared to traditional techniques based on quantum state and quantum process tomography. Finally, reinforcement learning, which is known to be
quantum state and quantum process tomography. Okay.
Very powerful machine learning technique.
So this is unsupervised learning. So within a system, you do that, and then you can use it for inference. Right. Okay. So. Right. Okay.
Which doesn't explicitly require data sets, either labeled or unlabeled, is also finding its place in the quantum many-body problem, especially as applied to quantum computing, and in particular for quantum error correction. So in quantum error correction, we try to find errors in the quantum device and correct them before logical qubits are corrupted. And there's many.
Okay, so I'm guessing this is what then Google took and ran with, and this is what they've implemented in their in their recent quantum computing.
Reinforcement learning techniques that are coming out that will be able to do this sort of quantum error correction in very fast time on classical processors.
Okay.
So as we go into the future, we have a toolbox made up of traditional numerical approaches, which have been developed for decades, but we also have a new toolbox based on machine learning that will be crucial in the characterization, preparation, and design of future quantum devices.
Okay, now it's starting to get interesting.
Dad?
Let's just keep it going. Yeah, let's see if somebody says makes more sense when they fill out some of the details. So gate model quantum computing, software stack problem definition, quantum algorithm, quantum circuit, quantum computer, QPU, and simulator. So quantum processing unit, and that's a quantum compiler and a simulator. So the Solovay-Kitaev theorem, finite set of gates can approximate any unitary operation, right? The gate model is universal, and quantum circuits is an X gate, the Hadamard gate, C0 gate, and you can essentially do all operations with just these three, if I remember correctly.
Talk about the gate model quantum computing, which is also called the universal quantum computing model.
Right.
The software stack of how you create an algorithm for a quantum computer is slightly different than what you are used to on a classical computer.
Okay.
So imagine that you have your problem definition. For instance, you want to solve the traveling salesman problem. That is, you want to find the shortest way of visiting n cities.
Right.
And then you can think about what is a matching quantum algorithm. Then you're looking into some optimization algorithm, for instance.
Right.
An algorithm that we are going to look into, which is called QAOA, Quantum Approximate Optimization Algorithm. This algorithm eventually splits into a quantum circuit consisting of gates and unitary operations. This is already a very low-level description. So if you're familiar with how a digital circuit decomposes, that's basically the level of what we are talking about here. But below this level, there's actual compilation going on. This compilation does mainly two things. One, if you have a set of gates and this set of gates is not implemented by the quantum computer, then it does a translation. So it considers actual set of gates implemented in the hardware. And the second thing it does, it's quite possible that you want to have some interaction between these two qubits, but these two qubits are not physically connected. Then it has to use all sorts of tricks to get around this problem. So it also addresses problems related to connectivity. We'll talk more about connectivity in the video on implementations. And once this compilation is done, then you can either execute your program on the quantum hardware, on the quantum processing unit, or on some simulator of the quantum system. Well, on a laptop, you can simulate maybe 20, 22 qubits. On a supercomputer, maybe 50. And that's pretty much when we run out of classical resources. So there is this fantastic theorem called the Solovay-Kitaev theorem, which says that you can approximate any unitary operation by a finite set of gates, and this approximation is efficient. You don't need that many gates. And this is what makes the gate model quantum computer universal, because you can take any unitary and you can decompose it into elementary gates, which just act on 1 or 2 qubits and reconstruct the effect of this unitary. So a digital computer is universal in the sense that it can implement any logical operation between strings of bits, whereas a quantum computer is universal in the sense that it can take any quantum state over qubits and transform it into any other quantum state over qubits.
All right.
So let's look at what exactly is a circuit? What happens once this decomposition is done and mapped onto gates and qubit registers?
All right.
So let's take a look at the simplest gate, the X gate, which just flips the 0 ket to 1 and flips the 1 ket to 0.
Right.
This is the equivalent of logical gate NOT. In a digital computer, that's our only single bit operation. But in a quantum computer, we have many single qubit operations. In fact, we have infinitely many, because we can map this any qubit on the surface on the sphere, which has continuous many values. So another important operation is the Hadamard gate, which takes the 0 ket and pushes it into the equal superposition. So this would be the equal superposition of 0 and 1. And it takes the 1 qubit and it maps it behind, which is basically the same thing but a minus sign here.
Yeah, I mean the phase transition is missing, so there needs to be one more gate.
So that's the way to create the equal superposition by applying the
repeat.
What? Oh my god.
Hadamard gate. And you can think of many other gates on the surface of the sphere. So let's look at a 2 qubit operation. The CNOT gate has a control part which detects whether the qubit that performs the control is 0 or 1.
Sorry, not phase transition, I mean phase shift.
And if it's 0, it doesn't do anything. And if it's 1, then it applies a NOT operation, an X operation. So the circuit representation is like this. So this is the control qubit. And this is where the NOT is applied conditionally. So for instance, if you take this qubit state, the 0, 0 state, where this is the control, then nothing happens because the control was not applied. On the other hand, if the control is flipped on, then it's going to flip the other qubit to 1. So now we can start thinking about preparing our first quantum algorithm, which would be the creation of the phi plus state, which is the equal superposition of the 0, 0 ket and the 1, 1 ket. So we see that we can easily create this, we can easily create this, but we want to create them at the same time. So what we do is we initialize 2 qubits in 0, 0. This is
okay, so you want to entangle, you want to create an entangled state.
Typical for a quantum computer. You always start your calculation in the 0, 0 state in every single qubit that you have. So now this is going to be our qubit 0. So our rightmost qubit, if you write it this way. So we apply a Hadamard gate on it. So at this point, what we have is an equal superposition of 0 and 1. And now we apply the control NOT. So when the control NOT looks at this one, it doesn't do anything. So the final state, we'll have the 0, 0 element.
So essentially, intuitively, the Hadamard just puts you into a single qubit. Your first control qubit is in a superposition of 0 and 1. Is it 0, is it 1? I don't know. It's 1 over square root of 2, 0 plus 1. And so when you hit the C0, you get a 50% chance that the wave function is 0, so you get 0, 0, plus a 50% chance that the state is in 1, so you get a 1, 1. So you either get 0, 0 plus 1 or 1, 1, so you get 0, 0 plus 1, 1, and nothing else.
And when it looks at the second part of the superposition, then it says that it's 1, which means it flips this qubit. So this is going to be the 1, 1 state.
Jolly good show.
And we have an equal superposition. So this circuit prepares the maximally entangled state with just 2 qubits.
Very good.
Today, the quantum computers that we have are fairly shallow in the sense that you can only execute gate sequences which have 10 or maybe 15, 20 gates. But ideally, you want to scale them up so you can execute an arbitrarily long algorithm. But that will be a long way to go. So later we'll talk about what you can do with these shallow.
No, that's good. That was 5 years ago, so it's improved. Again, it's also a question of the quality of the gates.
Well, what do we have here?
It's your last chance.
And Right, we have random stuff.
We introduced the gate.
So adiabatic quantum computing, unitary evolution and Hamiltonian, classical Ising model. So this is, I think, getting you to quantum annealers. So adiabatic. Yep, so you do that, you quench it, but it says this is universal. Interesting.
Modular quantum computer as a universal way of transforming quantum states into other quantum states. Today we are looking at a different model called the Adiabatic Quantum Computing, which can also achieve universal quantum computations, but to do this, we have to understand a bit more of the underlying physics. So we talked about Hamiltonians, which describe the energy of the system. We talked about unitaries, which describe the evolution of a system.
Right.
So let's go back to our classical Ising model, with the quantum mechanical description, where we have the sigma z operators acting.
Right.
So this was the energy of the system. It was the expectation value of the Hamiltonian in a particular quantum state. So if you just look at this, the Hamiltonian acting on the state has the exact same form as a unitary acting on it to get the evolution of the state. And there is actually a correspondence, and this is what is described by the Schrödinger equation. So it says that the temporal evolution of the system is described by the Hamiltonian applied to that state, that time-dependent state. Then you have the imaginary number here and the reduced Planck constant, but the main part is that the temporal evolution depends on the Hamiltonian. If you solve it, in the case where the Hamiltonian does not depend on time, then what you get is this formula.
The solution for the time-independent h is this. So when you do a d by dt, you get that. So why is this time-independent Hamiltonian? All right, because Hamiltonian is not, okay.
Which is exactly the unitary acting on a particular state for some duration t. So basically every unitary operation has an underlying Hamiltonian, and every gate in a gate modular quantum computer has an underlying Hamiltonian.
So it's time independent. If it was time dependent, it would not be this simple. So you want to push it into the regime where it is time independent.
And the Hamiltonian is always a Hermitian operator, which means that its adjoint is itself, which implies actually why this operation is unitary. So there's a very direct connection between the mathematical properties of these objects.
Okay.
So with that in mind, let's take a look at the adiabatic theorem. Imagine that you have two Hamiltonians. One, which I call H0, is just a transverse field. It's just transverse field acting on a number of sites. We know that the ground state, the lowest energy state of this, is the equal superposition. Now we can take another Hamiltonian, for instance, our classical Ising model. And they can take a time-dependent Hamiltonian, which mixes the two. So T starts in 0 and goes all the way up to 1. So T equals 0 is just the transverse field, and at T equals 1, it's only the classical Ising model. And if we change this time sufficiently slow, and we start in the ground state of this Hamiltonian, then we end up in the ground state of this Hamiltonian. And as I explained in the video on the classical Ising model, this is actually a hard problem to solve for nature, because
because if you go slowly, you start off where t is equal to 0, so it's 1 minus 0, it's h1. This is 0, so you start off in this one, and at the end of the day, you don't really care kind of what happens in between. If you go slowly, when t is equal to 1, this goes to 0, and you're left with h1. So,
It can happen that that the system gets trapped in a local optimum.
Mm-hmm.
Whereas here we are applying this trick, this adiabatic transition, to go from a ground state and ensure that we stay in the lowest energy solution throughout the change, and then we can read out the solution, the global solution of our problem. The caveat here is that there is a speed limit.
Speed limit.
A gap of a Hamiltonian means the difference between the ground state, the lowest energy state, and the first excited state.
Right.
And if we denote the gap by delta, then each and every one of the time steps in this change will have a different gap.
Okay.
You have to take the minimum of that and square it, and the speed limit will depend on the inverse of that.
Right, so the minimum delta, so it's the largest. Okay, so the speed limit depends. So every step that you take needs to be larger than 1 over the minimum gap. The minimum gap squared. So you've got a really small gap that gives you a big speed limit. Okay. And that depends on this. And this is depending on how you do it over here. So how do you calculate your delta gap?
So if there's a very, very close case of the excited state being very close to the ground state, then the speed limit can be very, very bad.
Right.
So it's not true that you can solve, say, NP-hard problems faster or exponentially faster.
Okay.
Because those problems, the hard cases, typically have a very, very, very tiny gap, which will imply that the speed limit is actually exponential.
Right.
So we can use this to perform universal calculations.
Perfect.
That's called adiabatic quantum computing.
Nice.
So in this case, the Hamiltonian has this part, which is just your classical Ising model.
Right.
And we have to add one more term, which is an interaction between transverse fields. So it's not the transverse field Ising model, because there the transverse field only acts on the individual sites. Here you have interaction between these transverse fields. If you are able to implement this Hamiltonian in the hardware, then this model can simulate universal quantum calculations, gate model quantum calculations, and therefore it can transform any quantum state into any other quantum state.
Okay, but I'm guessing that's where the tricky part is. Right, okay, let's keep going. Let's see what he has to say.
You did it.
What does he have to say? Why is it that D-Wave doesn't do that then? It's not so easy.
We talked about adiabatic quantum computation.
So quantum annealing. So minimum gap is hard to calculate. So anneal repeatedly, probably violating adiabatic conditions. Solve classical Ising model, experimental conditions, finite temperatures, and electromagnetic interference. So software stack, problem definition, map to Ising model, minor embedding, QPU. Oh, the chimera, yeah, I remember that, they had a chimera. And problem to solve. I'm not sure if they were able to move away from the chimera, they still do it.
As a way to exploit a phenomenon known the adiabatic theorem to perform universal quantum calculations. We can also do something slightly different. Adiabatic quantum computation is somewhat idealized. And a less idealized version is quantum annealing. So if you remember, to get the speed limit right when you perform the adiabatic transition, the annealing,
right,
you have to respect the gap and the minimum gap that you experience on all the Hamiltonians that you transition through. This is very hard to calculate. So the speed limit is intrinsically hard to get. So instead, what you can do is just...
Okay, I want to take a break. I'm getting hungry, so I guess this is part 1 of getting back into quantum computing. Yeah.